Hello everyone, welcome back to lecture 18 of Spatial Statistics and Spatial Econometrics. We are going to take the lead from the previous lecture where we had relaxed one of the assumptions of a classical linear regression model. In the previous lecture, we had relaxed the assumption that the model errors are homoscedastic, and we introduced heteroscedasticity into the variance covariance structure of model errors through the spatial dependence in prices of homes, for example, or groundwater levels, etc. Right? In today's lecture, we are going to take another step, and we are going to relax the assumption A2, which in lecture 16 we established as an assumption fundamental for causal inference. So to be able to move from correlation to causation, we require that the expectation, the conditional expectation of model errors is 0. That is, expectation ui given xi is 0, where xi is an explanatory variable. All right. And we also saw that that assumption is also important for unbiasedness of a least squares estimator. So in the previous lecture, what we studied was a generalized least squares estimator. Remember, that had got nothing to do with unbiasedness or causality. It was in order to reconcile the heteroscedastic model error structure. Okay. So before we sort of move forward and directly deal with the problem of causal inference, let's get back to specifying spatial dependence with the notion of spatial lags. So in the previous lecture, we had, that is lecture 17, we had said that we could imagine a classical regression model, a traditional regression model that we are used to, wherein each value of dependent variable yi has an index I which does not only provide us an ID for for whom this value y is measured, but also the location. So in that case, we could say y I j, which is equivalent to saying y at coordinates I comma j. So this enrichment of the notation is explicitly to account for spatiality in data. And then if you have a regular lattice, what is a regular lattice? Well, a regular lattice is where you have equal, you have a equi-sized cells, constructed by n rows and m columns in general. Okay, that is a regular lattice. That is to say that if I am I am considering the value of yi at any given cell, I will be able to find its neighbor in the north one step up, equal size cell. So if I take a step down, that is southward, I will find another neighbor. Similarly, a neighbor on the east and a neighbor on the west, right? So this idea can be notationally represented as what you have already understood. Shifting up would mean y I minus 1 and j, right? Then you have shifting down, we are calling it yi plus 1 j. So I is representing the vertical direction, downward south is conventionally taken to be positive. It is a it is defined that way. You could have also had it vice versa. Similarly, shifting left will give me the same I, but it will bring my j down from j to j minus 1, and on the right I will have yi j plus 1, right. So all of you are conversant with this by now. Now the issue is that this is a very stylized type of a spatial structure. The data don't always exist in such niceties so far as the spatial structure is concerned. A very good example or case in point is the groundwater monitoring data that we have seen throughout this course, right. So we have seen that data for the state of Uttar Pradesh. So if you pay attention, like I'm going to draw an approximate shape of of that state, and it looks like something like as following. It's not to scale, not to shape, it's just an approximation, right. And there, when we look at the groundwater data, we saw a very dense cluster of wells on the west, and when we move to south, you have a generally on the east we have a generally sparse monitoring network. and the monitoring network becomes denser around urban areas, right? So these are just our observations till now, okay? So in that case, we don't have the nice, representation of a regular lattice in case of a real world data. In that case, if we want to specify spatial dependence, we bring in the notion of spatially lagged variables, okay? So we bring in the notion of spatially lagged variables. So let's go ahead and look at an example where we will try to construct these spatially lagged variables for groundwater data. In order to construct spatially lagged variables, we formalize the local similarity for describing the structure of interaction among the spatial units. Okay, so that's a sentence which is saying quite many things. So let's break it down. Okay, so we're talking about the structure of interaction among spatial units. So we are trying to what are we trying to do? We are trying to describe a structure of interaction, and we are doing that through this idea of local similarity. Okay, so the fact that we believe in local similarity or local stationarity, we are designating, spatial neighbors as the ones which will also provide a spillover effect on the value that is being measured. Okay, so local similarity is in terms of the value observed, right? So the value observation, okay, value observed, or the groundwater level observed, the price observed, or whatever, right? We are describing it through the structure of interaction among spatial units. So we are saying that units that are nearby might have similar values. This is also the idea of local stationarity, right? So when we are constructing these spatially lagged variables, we are basically following up on the ideas that we have developed till now, right? So we are now formalizing it. So the quantitative unit that formalizes interaction with neighbors at any given location in space is called as the spatial lag. Very, very important. So we are now introducing an entity called as the spatial lag. It is an entity which formalizes interactions with neighbors for any given location in space. For example, I'm defining a spatially lagged groundwater level at location I. So I'm going on to location I, right? I am searching for its neighbors. So there are some wells which are located near to I, and there are some others which are located farther away from I. Okay, but I'm interested in the spatially lagged value at location I. Remember, the groundwater level that is observed at location I is given as G of I. Okay, we are trying to create a lag. So we are somehow summarizing information about what's happening around this location I. So GIL, where L is a representation of the spatial lag, is equal to WI1 G1 plus all the way to WIN Gn, which is equal to summation j equals 1 WIN Gj, right? I am able to provide a weight to each neighbor. So in case if, for example, we have this neighbor k which is really, really far away, right, and we don't believe that it's going to have any spatial dependence of groundwater level at k on what's happening at location I, then I can conveniently say Wik is 0. But that, specifying it to be 0 or non-zero is another matter. The point that I'm trying to make here is that this formulation of creating or constructing spatial lags by the help of these spatial weights, allows me to generalize the idea of neighborhood spillovers or neighborhood effects, right? I don't have to go in and specifically figure out who has how many neighbors. I can at least mathematically or notationally provide a general formulation of what a spatial lag means. So spatial lag is nothing but values in the neighborhood such that they are weighted by a factor Wij for the jth neighbor or the j unit which is a neighbor of I in the given domain, right? In this formulation, everybody is designated a neighbor, right? A unit which is which is proximate to I is also considered a neighbor. A unit which is farther away from I is also considered a neighbor. What differentiates these two units, which are proximate or farther away, is this weight Wij. And so this nice representation j equals 1 to n Wij, sorry for the typo, Wij Gj provides me a generalized formalization of the spatial lag effect. So if I am trying to understand what is the total extent of spatial effects on the groundwater level at location I, that I should study in relation with this spatial lagged entity summation j equals 1 to n Wij Gj, right, which concisely we write as Gi capital L. This capital L is just a lag representation. Okay. One thing to note here is that a location, any location is not its own neighbor. So location I is not her own neighbor. That means Wii will always be 0 for all I, for all I. Okay. So Wii will be 0 for all I. Okay. Even though Wii is 0, my general formulation doesn't change. I can always, for any I, be it I equals 1, 2, 3, 4, 5, n, I can use this formulation. The only matter of to understand here is if I am talking about the first location, location 1, location ID 1, then W11 will be 0. If I am talking about location ID 2, then W22 will be 0, and so on and so forth. Okay. So overall, constructing these spatial lags requires domain knowledge, right? But it summarizes pairwise interactions which would otherwise remain unidentified. Okay. So the spatial lag is characterizing pairwise interaction. So I and j in a pairwise sense, the way they interact is summarized by the spatial lag. It's a component of the construction of the spatial lag variable, right? But constructing it requires domain knowledge. How and why? Well, what value should Wij carry, right? Should it be just 0 and 1? Well, should it be, the nearer value should get larger, a value of weights than the ones that are farther away, and how much? By how much? What's the difference between different weights? Just because two points are equidistant to a location I, will they have the same spillover effect? Well, these are matters of complexities, and that's why if you are working with groundwater data, just like we have seen in case of stationarity, we require a lot of very strong domain knowledge. Here too, we require strong domain knowledge, right? So if you are working with groundwater data, it's best to work with hydrologists. If you are working with agricultural data, it's probably best to consult with agronomists and so on and so forth. If you are working with geological data like coal exploration data or oil exploration data, it's probably best to consult with geologists. If you're working with population density data, it's probably best to consult with population scientists, right? So whatever data set, whichever domain that your data set belongs to, one should read up the literature in that domain in order to do justice in defining these weights. Now potentially you have n times n minus 1 by 2 pairwise interactions, but only n groundwater observation locations. So you have a lot of pairwise interactions that you have to worry about, right? So for every I, there are n potential neighbors. Of course, herself is not a neighbor, so you can remove it, but in this formulation I am counting herself also a neighbor just because of the general form that I am studying. Just because Wi is 0, I am not keeping it out, I am just saying, because it's not her own neighbor, I is not her own neighbor, I can simply assign or define Wii to be 0, but and then keep my a formulation of GIL to be exactly the same. But potentially I have n times, so some n times n minus 1 by 2, which is much greater than n pairwise interactions to study, right? So if you have so many degrees of freedom and probably so many unknowns, so many parameters to estimate, then probably it's not going to be very efficient. I'm also providing a matrix notation of the same entity here. So I'm calling GL as a general, lag, spatial lag matrix. I'm not calling it GIL anymore. I'm calling it GL. Is a n by 1 matrix. So we can, we can write this down for our understanding. So I'm writing GL equals W times G. GL is considered to be n by 1, right? W is n by n and G is n by 1. So W is n by n and G is n by 1, right? So I have a lag matrix. So I have G1L, 2L, keep going, GIL, right? Okay. G1L, G2L, keep going till GIL, then I have finally GNL. This is a n by 1 matrix, okay. This is equal to a n by n matrix of weights. So this will, each row will correspond to the location 1, 2, I, n. On the columns, I am looking for neighbors. So everybody is neighbor to each other. The only thing is we have a weights understanding of them, right? So I have 1, 2, keep going, I, all the way till n. So columns are potential neighbors and rows are the entities for which we are trying to search neighbors for. This is again n by n, and then G is just the location, the column of values observed at each location in my data set. So now W1 and its neighbor W11, which is going to be 0, we have learned that. Then you have W12, W1I, all the way till W1N. So I have a weights, like row of weights sitting there as, W11. Then I have for 2, W21, W22, W2I, all the way to W2N. Similarly, WI1, WI2, WII, WIN, then WN1, WN2, WNI, WNN. Okay. So now I am multiplying a n by n matrix by a n by 1 matrix. As we have seen earlier, they are conformable, perfect. The overall product will be a n by, sorry about that. So they are conformable because the number of columns on the W matrix is equal to number of rows on the G matrix. When I multiply them, I am going to get a n by 1 matrix, right, something we are very well aware of. So let's write it down. So I have a n by 1 that I am looking for. So the first column is to be multiplied by the first row to find the first cell of this n by 1 matrix. So this is going to be W11, G1, W12, G2, W1I, GI plus W1N, GN. Similarly, the second one will be summation I equals or j equals 1 to n, W2j, Gj, right. So I am simply going to multiply the second row with the first column to get the second row of this n by 1 matrix. Similarly, I am going to have j equals 1 to n, Wij, Gi, and then finally the last element will be j equals 1 to n, Wnj, Gj, right. So now I can see that GIL equals the summation GIL equals summation j equals 1 to n Wij Gj, which is exactly the same as the scalar formation that we had seen on the previous page here. Okay. So, by now I am sure that you are very conversant between scalars and matrices, scalar forms and matrix forms of expressing the same linear equations. But, it's very critical to keep learning, keep improving our translation between the two devices. That's why I decided to sort of solve this for you. Okay, my request that you please go over this on at your own time so that it becomes absolutely clear, for your purposes, right? As we go forward, we are going to move to the matrix formulation more and more, because matrix is so concise. I mean, you have this type of a bulky GIL equals summation j equals 1 to n wij gj, such a bulky notation in scalar form for all i's going from 1 to n. All of these n equations, so you have n equations sitting here, are summarized in this simplistic matrix form, right? So, matrices are very useful, very handy when we are dealing with bulky notations. So, it's very important to learn to translate between scalar and matrix notations. So I request you to write it out at your own time so that it becomes more and more natural going forward. So, the next step is to construct a spatial weights matrix. So, now we look at an example where there are some spatial units, unit 1, 2, 3, 4, 5 and 6 are are assembled in a given spatial structure. What is the spatial structure? The spatial structure is such that 1 is neighbors with 2, with 4 and with 5. So, 1 is neighbors with 2, with 4 and 5. 2 is neighbors with 1, with 5 and with 4, right. So, 2 is also neighbors with 1, with 5 and with 4. 5 on the other hand is connected with 1, 2, 4 and 3. So, 5 has 4 neighbors, unlike 1 and 2, 5 has many more neighbors. So, 5 has 1, 4, 2 and 3 as neighbors. 3 on the other hand has only 2 neighbors, 5 and 6. 6 finally has just one neighbor, that is 3, right. Now, this is a complex spatial structure. There are entities distributed in space, right. Location is deterministic, it is not random. So, once you are located at as a neighbor of 2, 4 and 5, that is what it is for you, right. So, if it is a home which is a large mansion at location 1 and it is connected to a these 3 different homes, home 2, home 4 and home 5, then their location are sort of fixed. You can only sort of do as much in order to change the neighborhood of location 1, right. So, this is the spatial constraint that is driven by the links that are exogenously driven. We do not get to choose who is connected to whom. Okay. What we get to do is we get to summarize that in a spatial weights matrix. So, what does this spatial weights matrix does? First of all, you can see the diagonal elements are 0. These are WIIs which are 0. So, home 1 or location 1 is not her own neighbor, location 2 is not her own neighbor, location 3 is not her own neighbor and so on till location 6 not being her own neighbor. If we have 6 different entities, the size of the weights matrix is 6 by 6, right. We are working with a 6 by 6 matrix, right. Whenever we have a neighbor, we provide a weight of 1, and if they are not neighbors, we provide a weight of 0. So, if I go back to location 1, I had figured that 1 is neighbor with 2, 4 and 5. So, 2, 4 and 5 at locations 2, 4 and 5 in the columns I have 1s, and for the rests I have 0s at 3 and 6, right. Now, if I look at it, number of 1s that I find in rows, number of 1s provide me an understanding of how networked or how richly networked each location is. At an extreme is location 6, which only has one neighbor, which is number 3, right. So, 6 only has one neighbor, rest all are non-neighbors including herself, right. So, that is how a weights matrix is able to concisely account for the neighborhood structure. Now, we do not use these weights matrices. We define them as the way we have seen till now. Basically, we assign an entity 1 if j is my neighbor and 0 if j is not my neighbor. For each row, for each I in my data, I'm going to do that. But I then row standardize these weights. What does it mean to row standardize? It basically means that each row must sum to 1. Okay? So if I have a row with three ones and rest are zeros, I'm going to multiply each of these by the sum of what is found on that row. So each value of 1 is now normalized by 3, so it becomes 1/3, 1/3, 1/3. Of course, the zeros are also divided by 3, but 0 divided by 3 is just a 0. If I look at number 5, it has 4 neighbors, right? It has 4 neighbors, right? Now what I do is I sum the row, I get 4, I divide the whole thing by 4, so I get 1 by 4th, 1/4, 1/4, 0 and 0 in that row, in row number 5. Okay. Similarly, if I go and look at row number 2, again I have 3 neighbors overall for entity 2. I have only 2 neighbors for entity 3, so I have 1/2 and 1/2. I have 3 neighbors for entity 4 and I have only 1 neighbor for entity 6, so I have a value 1, that is 1 divided by 1, right. So this is called as, so W prime is known as the row standardized weights matrix. Okay, it's called as the row standardized weights matrix. A question arises, why do we row standardize these matrices? Why do we row standardize these matrices? Well, to understand that, let's look at the following model. This model is a spatial regression model. What's happening in this model is that I am multiplying, I am modeling G, which is a n by 1 vector, as a function of a lag of G, right. So this is GL, which is nothing but again a n by 1 matrix where W is n by n and G is n by 1, right. So I'm regressing G on GL, X, which is some exogenous variables, and then also Wx. So I'm not only spatially weighing the G values, which is the dependent variable, but also the explanatory variable. This is a very general structure that I have put in front of you. Okay. Now this is going to be n by k, so I have a n by k sitting here, right, and then I have the model error u, which is going to be n by 1. The parameters rho G and rho X are called as spatial coefficient parameters. These parameters explicitly account for the spatial spillovers, and beta is my model parameter, as I am already aware of, right. It's a coefficient sitting on each x value, right. U is just model error. Everything that I did not account for in this model will go into this U. U is going to be a random number. The question that we are asking is, why do we require W to be row standardized? Well, what happens is that I'm trying to understand the impact of of the lags, the spatial lag on the value at location I. So I want to know how much do groundwater levels in the neighborhood impact groundwater level values at location I. In this quest, you see in this formulation, this impact will be generated from 2 pieces of information. One is W and the second is G, right. What I'm really interested in is this G and not in W. That is to say that my quest as an analyst is not about understanding whether more neighbors or higher connectivity causes groundwater levels to increase or decrease, but to understand what happens with the levels in the neighborhood on the levels at location I. Because I want to connect groundwater levels with groundwater levels in a neighborhood, I want to normalize the effect of the number of neighbors. I don't want the effect to be driven by the number of neighbors. In case I do not use, I do not standardize WIs, then what happens is that just because some entities have 4 neighbors, this Wi value sums up 4 times, right? And just because some other entity has just 1 neighbor, which is entity 6 in our previous example, they will have a smaller spillover, just by the virtue of low connectivity. Well, that's not what I'm trying to learn here. I'm trying to learn the linkage between groundwater levels in a neighborhood on a location I, right? So in order to filter out the effects due to degree of connectivity, I am row standardizing my spatial weights matrix. Okay, so I hope that is clear. Now, a property of this spatial lag is that it is similar to but not the same as window average in case of a time series data. So I have an example of a time series of sales per quarter. Now, the time series is basically just joining all the different realizations of sales in different in quarters starting from 1986 to 1996 for some entity, right? The window average basically says go to quarter 3 of your quarter 4 of 1992 till quarter 1 of 1994, right? Basically take 6 quarters and sum everything between them. So this scanner will move step by step. This scanner will move 1 step here and it will look like the following at t. So this will be for t plus 1. Okay. So now this scanner basically just averages everything between these windows, and this moving average window is moving as we go along the time periods. Now spatial lag, if you think about it, is doing something similar. It's taking a weights type of a spanner or a scanner side of a window average type of a window, which goes through every value whenever I'm standing at a value I, and takes it just takes an average, which is a weighted sum, which is weighted average. The only difference is that here the value at the middle itself, which is here in case of this time t and t plus 1, these things are not counted in the weighted average, right? So the value at the location at which we are conducting this weighted average exercise or this window average exercise, that value itself is excluded in case of the spatial lag construction, right? So the fact that each location I is not her own neighbor means that the spatial lag is not a window average. It excludes the middle value. It excludes the value at the location where I am standing, wherein I am conducting a local average. Okay. Okay. So a little bit more into just a little introduction before we will go into these things. I just want to introduce some of these variables that are constructed for a regression model. One first is called as a spatially lag dependent variable. Now G being a function of rho Wg, this here is called as a spatially lagged dependent variable. Okay, and this, when it is added to a model that we are used to, which is x beta plus u, if I were to remove rho Wg, I will get a model that I am used to. When I include a spatial lagged dependent variable, such a model is called as a spatial lag model. Its a specific definition is it's a spatial lag model. Instead of rho Wg, if I were to include x beta plus rho x Wx plus u, then such a model which includes spatially lagged explanatory variable. So now I have lagged the explanatory variable, so I am saying the spatial effects are coming from the explanatory variable. So in case of house price data, the spatial effects is not coming directly from the prices of the homes in the neighborhood, but from the number of rooms in homes in the neighborhood or the public amenities for the homes in the neighborhood, right? So I'm sort of going over the example that we covered in the last class extensively, right? In that case, we call such a model as the SLX model or the spatial cross regressive model. And if instead we were to include these effects in the error structure such that u is rho wu plus epsilon, then such a model is called as the spatial error model. Going forward, we will go over each of these models, one by one. We'll look at what they mean, what is the consequence of including or not including these effects, how do we choose between these models, and so on and so forth. We will conduct that exercise. But for now, I just want, because we have introduced spatial weights, I wanted to, also introduce these three model variants of spatial regression models. Okay, so that's it for this part of the lecture. In the next part of lecture 18, we will be looking at what we started with, is the departure from the classical assumption of causality that ensures causality, that is assumption 2 of a linear regression model, and we will see how do we obtain causal inference in spatial regression models. Okay, so thank you very much and see you in the next part.